All right, so today we're going to begin our discussion of Dynamo, um, or we're going to continue really our discussion of Dynamo. For today's class, I asked you to read the Dynamo paper, and last time I talked a little bit about how this paper was important and influential. So back in the olden days, the assumption was that, of course, you would want to have strong consistency in your replicated storage system, and that was considered practically an answered question. Then Amazon came along, and they came out with this paper, which said we don't care about strong consistency. We're going to prioritize availability instead. Now, I have to say, I don't personally love the way that this paper is written. I think some parts of it just aren't well written, and there's a big chunk of text repeated in the first paragraph. That's something that should have been caught in a copy editing pass. Which is annoying, right? Like, come on, if you're going to write one of the most influential distributed systems papers of this millennium, at least have the decency to take a copy editing pass over it first. But it's a great paper to read in terms of how it connects with this class, and it touches on a whole lot of the concepts that we've already discussed. So now that you've actually read the paper, hopefully, what are some of the concepts that we've talked about so far in this class that play some sort of role in Dynamo? Sorry about that, had to adjust my headphones. All right, vector clocks are mentioned in there, good. Replication, sure, of course. Uh, these are good ones. What else? Byzantine faults, yeah, so Byzantine faults are mentioned, but only in the context of saying they're not going to worry too much about Byzantine faults. Um, Availability versus consistency, right, this is a big one. This is what we talked about before. Um, uh, a consensus model, probably what you mean there is consistency model. Tornadoes, the notion of a tornado hitting the data center. Yeah. All right. So availability versus consistency is probably the high order bit. So this is a big one. So how did we define availability? Our sort of first cut definition of it was all requests receive a response. But we could edit that to mean, say, all requests receive a meaningful response, instead of just a response like, I don't know, or I'm not going to tell you. And we might even want to put some time limit in there. Although I hesitate to specify any particular time limit. Um, so uh, um, if somebody wants to make an update, put something in a shopping cart, let's say, then the principle of Dynamo is go ahead and let them do it, no matter what. Network partition, no problem. You don't wait around to get acknowledgments from all the replicas. And if it means that there's some data loss sometimes, then so be it, because availability is what we want to prioritize. So network partitions are another big one. So we talked about network partitions last time. So somebody remind me what a network partition is. Some replicas can't communicate, right? So machines in some part of a network are unable to reach machines in another part. So network partitions are temporary and they're unintentional. So this is as opposed to a explicit decision to choose to not allow two machines to communicate. This is something that's temporary and unintentional. What else? What other concepts came up in this paper that haven't been mentioned yet? What did we talk about last time? Starts with E. Eventual consistency, yeah. So eventual consistency is an old idea. It's been around since at least the 90s, but it sort of had a resurgence as a result of Amazon or as a result of Dynamo and systems like Dynamo in the mid 2000s. So this goes along with high availability and network partitions, right? If you want to offer high availability and you want to offer partition tolerance, then you have to relax your consistency requirements. Now, as we talked about last time, this property of eventual consistency fundamentally belongs in a different category than those other consistency models that we talked about. So we talked about strong consistency and causal consistency and FIFO consistency. I wouldn't try to put eventual consistency in this same hierarchy. I'm a little bit of a hypocrite when I say this because there are some contexts where I do try to fit it into that hierarchy, including papers I've written. But I'm telling you, I think that it really belongs in a different category because all of those other consistency models are safety properties that rule out certain anomalous executions. And eventual consistency, on the other hand, is a liveness property. It's hard to say exactly what kind of safety property we get from Dynamo in terms of consistency. Let me write down a definition for this here. Uh, if updates stop arriving, replicas eventually come to agree. So I don't know what safety property we get from Dynamo. We talked last time about strong convergence, right? Which is the property that if two replicas have gotten the same set of updates, then their states will agree, even if those updates arrived in different orders. So that's a safety property. And that's a part of what's known as strong eventual consistency, which we talked about last time, which has both a safety component and a liveness component. But I don't think Dynamo actually claims to offer strong convergence in general. And the paper certainly doesn't mention this idea of strong eventual consistency. That was an idea that popped up a few years later. So by the way, Amazon didn't invent this concept. So I believe the term was coined by a guy named Doug Terry and his colleagues to describe a system that they built called Bayou in the 90s. But Amazon really popularized it to the point where now a lot of people think that Amazon invented this term eventual consistency. And a lot of people cite Werner Vogels, who wrote an article in 2008 called Eventually Consistent. A lot of people cite that article if they need a citation for this term, eventual consistency. I've been guilty of this myself. So public service announcement, if you're going to cite somebody for eventual consistency, don't cite the 2008 paper by Werner Vogels. Cite the older work by Doug Terry. Okay, so what else is in this paper that we've already discussed? Vector clocks were mentioned. Vector clocks. So how does Dynamo use vector clocks? keep track of version history, yeah, to give a logical timestamp to events. So when replicas differ, vector clocks are the first line of defense for conflict resolution, and Dynamo will try to use vector clocks to resolve conflicts. But as we've discussed many times, vector clocks can't resolve all conflicts because some events are causally independent or concurrent. So what does Dynamo do then when vector clocks aren't enough? Right, yeah. So there are two options, and both of those were just mentioned in chat. Timestamps or leave it to the client, right? So Dynamo either lets the client do the conflict resolution with their own conflict resolution mechanism that the client provides, or it uses last write wins. So it uses timestamps. So we talked a tiny bit about this application-specific conflict resolution thing last time. And the idea is that because the application developer presumably knows something about the data that they're storing and what kind of conflict resolution makes sense to do on that data, then they can implement their own conflict resolution mechanism that makes sense. So, for example, in the paper, we talked about resolving conflicts between shopping carts by taking their union, and then taking the union on the client side to get the final shopping cart. By the way, why did they pick set union and not set intersection? So we talked about this a little bit last time. Like, what if one replica thinks that there's a pair of pants in the shopping cart and the other one thinks that there's a book in the shopping cart? Why is it that you choose to take union on the client side and not intersection? To sell more product. Haha, that's the joke that I made in this class last year. So if you picked set intersection, right, you might lose some additions to the cart, right? Let's say one replica knows about both the book and the pants that I've added, and the other replica only knows about the book. If I then take set intersection on the client side, then if I take the intersection of book and pants and book, then the intersection of those two sets is just the set containing the book. Whereas if I were to take the union of those two sets, I would get the book and the pants. So either way, you might have a problem, right? You might make a mistake. If you picked set intersection, then you might lose some additions to somebody's shopping cart that had only made it to one replica. But if you picked set union, then you could also make a mistake because you might accidentally re-add some deleted items. Let's say that one client had added the book and the pants. Let's say the other one looked at that shopping cart, had received the whole shopping cart, and then said, oh, you know what? I don't want the pants after all. But then if you were to look at the two replicas and then take the union of those, then that deleted item would get re-added to the cart. So Amazon apparently decided that re-adding deleted items is better than losing added items. So we'll talk later on about mechanisms to handle deletion. Deletion is often very hard to deal with in distributed systems. Of course, Dynamo gets used for all kinds of things other than shopping carts. So set union doesn't always make the most sense to do. So that's why Dynamo allows you to provide your own conflict resolution mechanism. If you don't provide one, then fine, they'll just use last write wins in that case. Questions about that? Okay, so here's a question for you all. Let's just think about this case of shopping carts. So with shopping carts, we have this property that rights commute with each other, and so we don't care about the order in which they arrive. What does commutativity mean, by the way? So a binary operation is commutative if changing the order of the operands doesn't change the result. So for example, addition is commutative, right? So A plus B equals B plus A. So what do we mean by commutative when we're talking about rights? So when I say rights commute with each other, I'm sort of abusing terminology, right? Because I'm no longer talking about a binary arithmetic operation. But it's the same basic idea that the order of the rights doesn't affect the result. So in other words, if you're treating your shopping cart as a set and you add book and then pants, you'll have the same result as if you added pants and then book. That's what I mean. That's what I mean by commutativity in this context. The order of rights doesn't matter. So here's my question. With shopping carts, we have this nice commutativity of rights, and that by itself is enough to give us strong convergence, right? But the paper also talks about vector clocks. So why do we also need vector clocks? Because normally, vector clocks would be for enforcing causal consistency or causal delivery, right? Or some sort of causality-related property. But they didn't promise causal consistency in this paper. So why have vector clocks? If you're doing shopping carts, what do you still need vector clocks for? What do you think? Okay, somebody mentioned keep track of who put what in the cart first, but does it really matter who put what in the cart first if it doesn't matter? Okay, so there's a good point here. How are shopping cart operations commutative if you can do deletions? Right, yeah. So I think that the use of vector clocks in Dynamo is to try to minimize these sort of deletion anomalies that can occur. So the vector clocks are able to rule out most, although not all, deletion anomalies. You're still occasionally going to have a deletion anomaly, and they say that they're okay with that. All right. So every now and then, you're going to get into this sort of situation where replicas disagree. And maybe even one of them has an update that is causally later than the other according to their vector clocks. Or maybe they disagree because of concurrent updates that aren't resolvable using vector clocks, whatever. But one way or another, replicas disagree. Well, okay, so one of the challenges here is even finding out that replicas disagree in the first place. Because going back to that example that we've sketched out before, where you have two clients and two replicas, and you have differing rights, we can see from looking at this picture that replica 1 and replica 2 disagree, but they don't know that they disagree. So job 1, right, is to even notice that they disagree. And then after that, they still have to figure out how to resolve the conflict. So even finding out that replicas disagree with one another in the first place is hard. So if we're drawing Lamport diagrams like this, we have a sort of God's eye view of the whole situation, which is a great luxury, right? If you're actually trying to build and debug distributed systems, as you know, you don't have this lovely God's eye picture. We can see that there's disagreement, but the replicas can't. So this replica, which thinks x is 3 right now, has no way of knowing that somebody else thinks x is 4. So Dynamo has a couple of mechanisms in place to allow the system to try to find out about and resolve such conflicts. So one of those mechanisms is what's known as anti-entropy. Can somebody who recalls what this was in the paper tell me what it means? Yeah, so anti-entropy is a protocol that you can use to try to keep replicas consistent. How does it work in Dynamo? In Dynamo, the way it works is that once per second, every node randomly picks another node and contacts it and finds out what its state is. Actually, to be very clear, there are two different things being discussed here. When the paper talks about anti-entropy, it's talking about resolving conflicts in replica state, meaning the actual key value pairs being stored. Because Dynamo is a key value store, right? So anti-entropy is for resolving conflicts in replica state. And replicas randomly contact other replicas at a regular interval to find out their state. So this is distinct from something else that the paper talks about. The paper also talks about something called gossip, which is related but different. When the paper talks about gossip, it's talking about it's also talking about communication between replicas, but it's not about replica state in terms of the actual key value pairs being stored. Does anybody remember what gossip is used for in this paper? Remember when we talked about different problems that all amount to consensus problems? One of the problems that we talked about was the group membership problem. So this had to do with that. So what does Dynamo use gossip for? Looking at other nodes' routing tables, yeah. So in other words, it wants to know what nodes are actually participating in the system, and what does it think the other nodes, what do the other nodes think the other nodes are, right? So this is another kind of state that has to be kept consistent between replicas. In addition to the actual data being stored, these key value pairs, they have to keep track of what nodes exist, right? And in Dynamo, this is done via gossip. So gossip is for resolving conflicts in the view of membership. So two different mechanisms, but they're for resolving conflicts in different kinds of state, right? Anti-entropy is for resolving conflicts in key value pairs. Gossip is for resolving conflicts in what do the other replicas think the current set of nodes are that are up. So that's what gossip does. So a node contacts another node to say, hey, what's your view of who's up and running right now? And gradually they all figure it out. So membership here means who is up and running. So what's interesting about this paper is that they say that they actually used to have a mechanism that maintained a globally consistent view. But they figured out that they didn't need it. And so they do gossip instead, and that ends up being good enough. So I find this to be interesting. They used to have this mechanism for maintaining a globally consistent view. Maybe they had some centralized configuration server that everybody would talk to find out what the current view was. And that probably ended up being some kind of a bottleneck. And so they figured out that they didn't need that. So they ended up using this gossip mechanism instead. And so just like the current view of the data is eventually consistent in Dynamo, the current view of membership is also eventually consistent in Dynamo. And that turned out to be good enough for their needs. So Dynamo has these different mechanisms in place for resolving conflicts in application state. So let me say here, application. Application state, meaning the actual key value pairs being stored, and conflicts in group membership state, meaning a node's view of what other replicas are up and running. And these mechanisms are called anti-entropy and gossip, respectively. So this happens to be the way that this paper uses these terms. Sometimes you'll see people use these terms as synonyms, and anti-entropy is just a fancy word for gossip. But in the context of this particular paper, they happen to mean different things. Okay, so gossip and anti-entropy are both for resolving conflicts in some kind of state. But here's a question for you. Practically speaking, how are these two problems different? How is resolving conflicts in application state different from resolving conflicts in group membership state in terms of practical implementation concerns? So these are conceptually very similar, right? And really the question that I'm asking has to do with the amount of state that's being sent between replicas. So the states, like think about what information we have to send back and forth in the case of these two situations. So with gossip, if you ask somebody else, hey, what replicas are up, right? It's a pretty small amount of data that has to be sent back. But if you ask some replica, what are all the key value pairs that you have? The amount of state that has to be sent back is much, much larger. So with group membership, you really just have this kind of small number of nodes. You have this set or list of some relatively small number of nodes. But for application data, application state, you could have a lot of key value pairs. So given that the states are so large, this right here, find out their state, this could be pretty hard to do. It isn't going to be feasible for replicas to send their complete state to each other all the time, once per second. That would end up being pretty expensive, and you would flood your network with just these anti-entropy messages. So what does Dynamo do instead? Instead of sending the complete state to other replicas all the time, what do they do to minimize the cost of data transfer for this anti-entropy process? Right. They use something called Merkel trees. Also known as hash trees. So a Merkle tree looks something like this. So let's say you have some pieces of data. I'll draw it from the bottom up. So we'll call them 1, 2, 3, and 4. So these are just pieces of data, any data. In our case, they would be key value pairs, but Merkle trees don't require this to be about key value pairs. You could use any kind of data here. So these are just pieces of data. So at the leaves of the tree, you have hashes of each chunk of data. And then for the non-leaf nodes, every node is going to store the hash of its children. So in this case, you would do something to concatenate or otherwise put together these two hashes and then take the hash of that. And similarly here. So let's call this whole thing A and call this whole thing B. And then the parent of these would be the hash of A and B concatenated or otherwise put together. And then that's the root. So at the leaves of the tree, you have hashes of each chunk of data. And these would be, maybe sets of key value pairs or whatever else. And then at the non-leaf nodes, each node is going to store the hash of its children. This one happens to be a binary tree, so non-leaf nodes have 2 children. And they might, for instance, concatenate their children's hash values and then take the hash of that, and so on up to the root. What is the purpose of doing this? Yeah, so the problem that we're trying to solve is this cost of data transfer problem, right? We don't want to have to send our entire state over to another replica, right? So if we have 2 replicas, each storing lots of key value pairs, and let's say that they differ in the value of just 1 key, right? It would be really, really expensive to have to send the entire state from one replica to the other to compare it, especially since there's just only this one point of disagreement. So if you had this, let's say replica 1 and replica 2. So let's say replica 1 had like x equals 3, y equals 4, z equals 5, q equals 7. And let's say replica 2 had almost exactly the same data, but differed in one place. So let's say but how are you going to quickly find out that there's only this one point of disagreement? Well, that's where you can use Merkel trees. So in this case, say these are our data items. So you'd take the hash of each of those. So you'd have so I'm going to put a tick mark here to show that this one is different. So when you combine these two, you get this single hash value. And so these are going to be the same, but these are going to be different. And so the root, of course, is going to be different because one of the children is different. So if this is A and B, and this is A prime and B, So this thing, the root, is the thing that gets sent around from replica to replica at first. So replica 1 wants to know what replica 2's state is. Replica 2 can send over this hash value to replica 1, which is just one number, right? As opposed to having to send all this data. Replica 1 can look at it and see, oh, that hash value is different from mine. Okay, I see that it's different, so I know now that our replicas differ in at least one key value pair. Okay, now send me your children. So then replica 2 can send over these two children. Replica 1 will look at those, compare it to its own children. It'll see that this one is the same, right? Its value for this, this child is the same. And it'll see that this one is different. At that point, it knows that everything under this branch of the tree is going to agree. So it doesn't have to worry about that anymore. It's now ruled out half of the key value pairs as key value pairs that it doesn't have to worry about synchronizing with replica 2 because it knows that they already agree. It now knows that the disagreement is going to be somewhere in this branch. So it's cut down the size of the search space by half. So then it can dig further down and compare the children there. So then it'll see that this hash value differs for this particular one. And then finally, at that point, it can see that those two differ. And again, it's just comparing numbers, right? So now it can see that they differ, and now it says, okay, send me your value for key Y. And to make it even more clear why this is useful, in Dynamo or in many key value stores, these keys, or the values that are stored at these keys, they're not necessarily just numbers like 5, right? They could be arbitrarily large objects. So having to actually send over the value associated with the key, even just one key, could be somewhat expensive, right? Depending on what's actually being stored in the key value store. So it could be somewhat expensive to send over that whole object, compared with the cost of having to send over one little old, say, 32-bit hash value. So you save a lot of bandwidth by comparing hashes and only having to send over the data for values that actually differ. So Merkel trees are this mechanism for quickly finding out where the point of disagreement is between these replicas. So in this case, only this one data item is different on these two replicas, and so the parent will be different, and then the parent of that will be different, and finally the root will be different. So to compare their state, you can begin by comparing the root. If it's the same, great. You then know that all the underlying data is the same. If not, then you have to compare the two children. And in this case, child A will differ while child B will agree. So you can then focus in on A, look at its children, then figure out that it's this particular item that differs. And we figured that out by just sending a few small hashes over the network instead of lots of data. So a question in chat just now was, well, what if there's more than one hash that's different between each of the replicas? Sure thing, yeah, that could happen, yeah. So Merkel trees only help, right? They help in the case where there's only a small difference between these replicas, right? So if a lot of keys differed, then both of these children might differ from the corresponding children on the other side, and all these children might differ as well. So in the worst case, you do end up in the situation where you have to send over all the data, right? But you have to do that anyway, right? So Merkel trees are especially useful in the situation where you expect the replicas to be mostly caught up with one another. And they're handy anytime that you need to compare large data sets. So often you'll hear Merkel trees discussed in a context of data analysis and comparing large data sets. They're especially useful if you need to do so over a network, right? So they're used in all kinds of systems, not just in key value stores. You'll often hear them discussed for properties of verification, right? Like if somebody has some data, somebody else has some data, and you want to ensure that they got the right data, right? Then you can compute this hash value by taking hashes of individual pieces of data and then the parents of those and so on until you get this this hash value that can be used as a sort of checksum. And then you can, and then if the checksums turn out to differ, you can figure out exactly where those two pieces of data differ. So that could be used for security, right? You could try to figure out, you could use this mechanism to figure out if your data has been messed with. And so Merkle trees are often discussed in this context of authentication, right? To make sure that, that your data hasn't been messed with. Now in this paper, they're kind of leaving aside that whole question of authentication, right? They're talking about replicas that are in an Amazon data center. They're not untrusted, right? So in this paper, they're only using Merkle trees for this, for the purpose of saving bandwidth between replicas. So they're not worried about so much about the case of data getting corrupted by some attacker, right? Which is the context in which you often hear Merkle trees discussed. They're only worried about saving bandwidth. So it turns out Merkle trees are useful for solving both of those problems. Okay, so there's a couple more questions in chat here. Somebody asked, how do they decide which of these values is more recent, right? So yeah, so you can store a timestamp on these elements. You could store a vector clock and compare those. But you know, job one, right, is finding out that replicas differ at all. Then finding out how to resolve the conflict is another question. And we talked about strategies for that. Maybe you don't resolve the conflict. Maybe replica 2 says, oh, I have 5 for y. And replica 1 says, oh, okay, I guess I'll store both 4 and 5. And then if the client wants to know what y is, I'll give the client both. So that's an orthogonal problem, right? This question of how do you resolve the conflict? So Merkle trees help with the first problem, which is finding out that there is a conflict at all. So one question that came up when I taught this course last year, and I drew this picture on the board, somebody asked, well, in this case you have X, Y, Z, Q on both of these replicas. So what if one replica had a different set of keys? Like how would the replicas know like what if a replica has a different set of keys than the other replicas? Then how do you construct these Merkle trees? So this is like the standard picture that people usually draw when they talk about Merkle trees. And so if you were to Google for Merkle trees and do a Google image search, you always see this thing that looks like a binary tree. So, but there's this great question, right? How does this Merkle tree thing work if the replicas don't know about the same set of keys? So in the Dynamo paper, it seems like the answer is all the replicas know which key ranges they're supposed to be responsible for. So they can just have an entry in the Merkle tree for every key in the range, whether or not there's actually a value associated with that key. And these ranges are pretty big, right? So you might want to try to use some efficient representation of the tree for the tree to be of tractable size. So that's one thing that you could do. But a more interesting answer might be that instead of storing the data in this binary tree, instead you would use what's known as a prefix tree or a trie or whatever it is that you choose to call it. So a prefix tree is keyed on hashes of the keys. Don't confuse that with these hashes. So these hashes are hashing the values, right? And that's the whole point, right? That we want to see if the values differ between replicas. So in a prefix tree, you get this thing where you have hashes of keys, and then you can look up a key in the data structure by its hash. So there's two different, if that's what you were doing, if you had a prefix tree and you were also doing this thing of hashing the data for quick comparison between replicas, there's two different kinds of hashes being talked about. This took me a while to get my head around. So the resulting data structure is a prefix tree that's also doing this thing where it's hashing the data. So you might call it a Merkelized prefix tree, or my favorite, a Merkelix tree. So Merkel plus prefix tree is known as a Merkelix tree. So this is a term you might have heard. Blockchain people talk about it a lot, but it's not just for blockchain stuff, despite what blockchain people might have you believe. So my former colleague Graydon Hoare told me that this Merkelix tree was in fact the data structure that he implemented when he was implementing a version control system called Monotone back in the early 2000s. And this is what he used for synchronizing copies of objects. So, and he just called it a Merkelix tree, or he called it a Merkel tree because it didn't occur to him that there was a version that wasn't also a prefix tree. But Merkelix tree is the silly name that some people use for that. So that's kind of my answer to this question of if replicas had different set of keys and you didn't have this ahead of time knowledge of who was responsible for what key ranges, then you could use Merkelix trees. And then you would determine that that replicas have different sets of keys by just looking at the structure of the prefix tree. And then for keys that disagree on value, you could use you could use the hashes of the values. That doesn't seem to be what Dynamo actually does, but it was for me it was worthwhile for me to learn about this anyway. So I'm sharing it with you as well. Okay. So let's do a quiz question. Let's talk really briefly about last time's quiz question. So last time our question was just, what does it mean for a replicated storage system to be strongly convergent? So the definition of strong convergence is replicas that have received the same set of updates have equivalent state, regardless of the order in which those updates were received. So it's a safety property. And here is today's quiz question. So there was just a question on Twitch about hash collisions. So sure. So what would happen if you had a hash collision? Well, let's say that you had a crappy hash function, and the hash of 4 and the hash of 5 here ended up being the same. Well, yeah, indeed. Then this update might not make it to the other replica, right? So this mechanism is dependent on you having a good hash function. So I suppose if you wanted to decrease your vulnerability to that, then you could try having multiple uh, anti-entropy mechanisms using different hash functions. Of course, then you have to store the results of those different hash functions. But I think no, I think like a standard good quality hash function turned out to be good enough for their needs. And they didn't care about it being a cryptographically secure hash function because, again, they weren't concerned so much with security. They weren't concerned with ensuring that that the data didn't get corrupted by an attacker on the way from one replica to another. Instead, they were just concerned with making sure that the replicas were up to date. Okay, so in the 5 minutes that we have left, I want to quickly touch on one more concept, which came up in the paper, and which is very useful to know about. So this is a concept of what's called quorum consistency. And we won't have time to discuss this fully today, so we'll talk about it more next time. But let's just touch on it. So in primary backup replication and chain replication, clients would only talk to particular nodes, right? In primary backup, the client only talked to the primary. And in chain replication, the client would talk to the head and the tail. The head for writes and the tail for reads. But in Dynamo, the client can actually talk to any replica or all of them. So no replica is playing a distinguished role. So suppose we have a client and 3 replicas. And the client is actually aware of the identities of all these nodes. So in some sense, the client kind of starts to resemble the primary from primary backup replication, right? Because the client can go out and talk to all these nodes and get responses from all of them. But how many does it have to talk to? So in quorum systems, which is what Dynamo is, this is actually something that's configurable. So how many should I talk to? So there are 3 important variables. So n is the number of replicas. In this case, 3. W is the number of replicas that have to acknowledge you before you can consider a write operation to have completed. Also known as the write quorum. And R is the same thing for reads. That's the number of replicas that have to acknowledge you that before you consider a read operation to have completed. Or the read quorum. So W and R are both going to be at most n, right? but they could be less than n. So let's think about some different combinations of W and R. Let's suppose that in this 3 replica system, we set W to 3. So 3 replicas have to acknowledge a write. And let's say that we set R to 1. If we did that, so if W were 3, and R was 1, do you think that would give you strong consistency? Somebody says no. Somebody else says yes. Yeah, so it actually would. So if 3 replicas need to acknowledge a write before you consider that write to have completed, then if you write to all 3, then if you do a read, you know that you're going to read that write. So this is a very popular setting, sometimes called write 1, or excuse me, read 1, write all, or RAWA. So this actually does give you strong consistency. But what's wrong with it? Well, it's not fault tolerant in the sense that if a node crashes, or if there's a network partition that separates a node, some nodes from the client, then the client can't do any writes, right? Because the client has to write to 3 before the write is considered to have committed. So this is not necessarily the best setting for all situations. We're out of time, so we're going to come back to this and we're going to talk about it much more next time. I will see you on Wednesday. Take care.